Welcome to The Explainer. Today, we're diving straight into one of the absolute most foundational and honestly most powerful data structures in all of computer science. We're talking about the graph. By the time we wrap up here, you're going to see the digital world in a totally new, highly structured way.
Think about this for a second. When you log into a platform like LinkedIn, how does it actually know who you know? How does it instantly suggest those second or third degree connections, or pinpoint the exact communities you belong to out of literally billions of users? Well, it feels like magic, right? But actually, it's just incredibly elegant computer science at work.
To really get how this works, we just need a little bit of real-world intuition. So in a digital network, you, the user, are what we call a node. And your connection, your friendship or professional link to someone else, is represented as an edge. That simple pairing, nodes and edges, is the exact engine powering the biggest networks on Earth.
Which brings us to the official definition. A graph is a data structure composed of nodes, sometimes called vertices, that are connected by edges. We use graphs to model relationships, and those edges strictly define how the nodes interact with one another. It is, quite simply, the ultimate tool for mapping out connections.
Okay, here's our roadmap for today. First, the anatomy of a graph. Second, graph attributes. Third, representing graphs. And fourth, traversing the network.
Section 1. The anatomy of a graph. So one of the very first terms you've got to know is degree. The degree is simply the number of edges connected to a single node. You'll also hear about adjacent nodes, or neighbors, which are just two nodes directly connected by an edge. Let's actually visualize this so it clicks. Check out node 0 at the top here. Notice how it has 3 lines coming right out of it? That means its degree is 3. Those lines connect it directly to nodes 1, 2, and 3, which are circled with that blue dotted line. Those are its adjacent nodes, its neighbors. Now look over at that orange highlighted route going from node 3 down to node 2 and then over to node 4. That sequence of nodes, connected by edges, is what we call a path.
Section 2. Graph attributes.
There are 3 primary variations, or flavors, of graphs that you're going to encounter all of the time: directed versus undirected, weighted versus unweighted, and cyclic versus acyclic. Let's break down exactly what these look like.
Starting with directed graphs. See those arrows on the edges? This means the relationship has a specific direction. It's kind of like following someone on social media who might not follow you back. Next, we have a weighted graph. The edges here actually have numbers associated with them, like 6, 12, or 10. These weights could represent the physical distance between 2 cities, or maybe the cost to route data between servers. Finally, we have a cyclic graph. Look at that orange highlighted triangle connecting nodes 0, 2, and 3. A cycle is simply a path that starts and ends at the exact same node. If a graph doesn't have any of these loops, well, it's called acyclic.
Section 3. Representing graphs.
So how does a computer actually store this visual information in memory? Well, it usually comes down to one of 2 common blueprints. First is the Adjacency List. This is often implemented using a hash map where the key is the node and the value is a literal list of its neighbors. Look at row 0. Its neighbors are 1, 2, and 3. Super straightforward. The other option is an Adjacency Matrix. It represents the exact same graph but uses a 2D grid instead. If there's an edge between node 0 and node 1, you'll see a 1 where row 0 and column 1 intersect. If there's no edge, there's a 0.
Now, why choose one over the other? It really all comes down to efficiency. Adjacency lists are definitely the most common choice. They're fantastic for representing sparse graphs, where nodes don't have too many connections, and they're absolutely perfect when you need to efficiently iterate over a node's neighbors. Adjacent matrices, on the other hand, are the go-to for dense graphs. That's where almost everything is connected to everything, and you have to perform extremely frequent, rapid checks just to see if a specific edge exists between 2 nodes.
Section 4. Traversing the network. Okay, so now that we have our nodes and edges stored, how do we actually search through this web to find what we're looking for? Well, we use 2 primary traversal techniques. The first is depth-first search, or DFS. The logic here is typically implemented recursively. You start at a node, process it, and then dive as deep as possible down one path of neighbors before backing up. But, and this is a huge but, you absolutely must keep track of the nodes you've already seen using something like a hash set. Why? Because if your graph is cyclic and you forget to mark nodes as visited, your program is going to get stuck in an infinite loop. Nobody wants that.
The second major technique is breadth-first search, or BFS. Instead of diving deep recursively, BFS is typically implemented iteratively using a data structure called a queue. You add a node to the queue, pop it off, process it, mark it as visited, and then append all of its unvisited neighbors to the back of the queue. So what does this mean in practice? It means BFS explores the graph layer by layer, moving uniformly outward from the starting point.
Let's demystify the performance here. For both DFS and BFS, the time complexity is big O of n plus e. But what does that actually mean? Well, n is the number of nodes, and e is the number of edges. Your time just scales linearly because during a traversal, you visit every single node once, and you explore every single edge once. It's incredibly efficient. For space complexity, both use big O of n. DFS takes up space in your computer's memory because of the recursive call stack, while BFS takes up space because of the queue holding all those nodes waiting to be processed.
So look how far we've come. We've gone from the simple concept of nodes and edges all the way to recursively traversing complex networks in memory. Social networks like LinkedIn are really just the beginning. GPS routing, internet search engines, recommendation algorithms, literally all of them rely on the exact data structure we explored today. So the real question is, now that you know what to look for, where else are graphs hiding in your digital life? Keep your eyes open, because I promise you, they are everywhere. Thanks for joining me on this explainer, and keep learning.